in perhaps they should be called subsections. In 12.4, there are 3 subsections. There's the multinomial distribution. Now, the binomial distribution was on the first midterm. That doesn't mean that you can forget it completely, because it's still been coming up. It comes up in connection with approximations to it, among other things. Yes, so the binomial distribution is still a live topic. Geometric distribution. And the last of our discrete distributions, Poisson distribution. And so, of course, for each of these, we want to know how to use them and when to use them, what they apply to. There are 4 subsections under 12.5. One on continuous random variables in general. So this brings in concepts like the density function. The expected value is you get by a certain integral, variance as an integral, cumulative distribution function, the uniform distribution, where we're picking a number at random from some interval, and the density function is just flat. The exponential distribution. This can be viewed as the waiting time to the first hit in a Poisson process. Like the geometric distribution is giving us a waiting time for Bernoulli trials. And then we talked about modifying the exponential distribution if the hazard rate changes with time. And lastly, the normal distribution. Which, of course, is closely connected to the last of the 8 sections on the central limit theorem. For sums and averages, of independent, identically distributed variables. Because the central limit theorem says the normal distribution applies in this situation and talks about, what the mean and the standard deviation is going to be. Well, so this is the list of topics. One might ask, well, is there anything that we don't need to know? Well, I hunted through the book. It was pretty hard to find anything in this category. I think I found one page. It was page 879 on generating random numbers. So we have ignored that topic. Let's continue to ignore it. It's pretty specialized. Besides, computer programs do this much better. But to balance that, what we do need, which is not in the book, or is in the book only and mentioned in passing, is the fact that a binary random variable has standard deviation no more than a half. Well, this is mentioned on page 896, but only very briefly. And of course, by binary random variable, I mean that the range is 0, just consists of the numbers 0 and 1. Well, do I have any useful advice for this midterm? Well, just sort of the usual things. Like, read the problem. Well, what I mean is, these problems, yeah, we have a certain number of sentences. And the problem is to figure out, what are these sentences telling you? If it says that something or another is point 2, where in the picture does that point 2 go? Is the problem describing a discrete random variable or a continuous random variable? Or neither of the above? Not that the dividing line is always sharp, because in some cases it's, for example, in the normal approximation to the binomial distribution, the binomial is the number of successes is a discrete random variable, which we might want to approximate by using a continuous random variable in the normal distribution. Are those sentences talking about Bernoulli trials? And if so, what random variable is involved? Are we talking about the number of successes? Are we talking about the number of trials, the waiting time for the first success? Or even for a second success? Is it talking perhaps about the sum or the average of some large number of trials? In which case we might want to bring in the central limit theorem. Or perhaps is it describing a Poisson process? Well, the word Bernoulli, the word Poisson may not occur in the problem, but we know how to recognize these situations. If it's a Poisson process, what random variable do we want to apply? Is it counting the number of hits? Is it perhaps the waiting time for the first hit? Those lifespan problems come up in here, where the first hit is fatal. Yes, for that matter. Yeah, is it a lifespan issue? And if so, yeah, is the hazard rate constant? Is the hazard rate changing? Well, we know how to handle both of these. Well, a couple more things on this list. Is the problem talking about perhaps an average or perhaps a sum of independent, identically distributed random variables, or say independent, identically distributed measurements? For that matter, if we're given some equation for some function, is that a density function or is it a cumulative distribution function? Well, these two are related, and if we know one, we know how to find the other one. Okay, but we want to keep straight which is which. Well, this is what I have in mind by saying, there's reading the problem and there's analyzing what those sentences are telling us. Can we express the information perhaps in more directly usable form by algebraic equations or such? Well, I thought I would work some problems today. Are there questions about the midterm or such that people wanted to bring up? Plunging on. Some of our problems are the following of form. Well, let's look at the case of a normally distributed random variable, say x. Normally distributed with mean, which we'll call mu, and standard deviation, which we'll call sigma. Often we're looking at the following equation: the probability that x is between a and b is some number c. I claim that knowing any four of the 5 numbers here, if we know any 4 of sigma, mu, sigma, a, b, and c, we can find the other one. Well, at least that's almost true. Solving for mu can be awkward. Might have to resort to successive approximations, but there's the homework problem number 28, solving for sigma. We've done problem solving for, well, at least for, yes, for A, B, and C. For example, let's do a solve for B problem. So there's a normally distributed random variable, and what if we know those other four numbers? Say the mean is 10, the standard deviation is 5. We want to find a number t probability that x is between 0 and t is 0.9, 90%. Okay, so it's this equation, but a solve for B problem. Well, so let's do this. Have these numbers. Well, step 0, let's draw the picture. It'll give us some idea of where t needs to be. Normal distribution with mean 10, standard deviation 5. So the density function centered at 10, and it has these inflection points at 5 and 15. We want this probability to be 90%. So t is going to have to be more than 10. The probability that x is 10 or less, I mean, that would only be a half, and from 10 down to 0 would be even less than that. So to get 90%, yeah, we'll need the area up to 10 and then some. So the problem is telling us that something is 0.9. Namely, that area shaded in red is what's 0.9. And when we work out t, it had better be something bigger than 10. Well, that's step 0. Just look at the picture. On to step 1. We need to follow our usual procedure. That is, we standardize this normally distributed variable, and we look up the numbers in the table. So yeah, this probability has to be 0.9. So to standardize, we subtract the mean throughout. The mean is 10, so we'll subtract 10. And we'll divide by the standard deviation. Well, and then this is an equivalent inequality. So it's the same event. The probability is still 0.9. We haven't changed the event. But what we have done, we simplify that to -2. And x minus 10 over 5 has the standard normal distribution, call it z. So this can be written in terms of the capital phi function. It's phi of t minus 10 over 5, which we don't know what that is yet, minus phi of minus 2. Well, at least phi of minus 2 we can look up in our table. Not directly, but we can look up phi of plus 2, and we know how to convert. So let's update the picture. We now have the standard normal distribution for z. So it's centered at 0, and the inflection point's at plus or minus 1. Minus 2 is down here. And we're looking for a number, it's got to be positive. T minus 10 over 5. And we still have that red area that has to be 90%. Well, phi of minus 2, that's 1 minus phi of 2. So we look up phi of 2 in our table. 1 minus that, 0.0228. So phi of minus 2 is this left-hand tail in this picture here. It's not very big. So this equation, solving for the thing we don't know, but don't know yet, phi of t minus 10 over 5, the thing we don't know, we'll put that on one side of the equation, and the things we do know can go on the other side. It's 0.9, okay, plus 0.0228. So we look at our table for a number, phi of which would be 0.9228. Well, we don't find anything that works perfectly. Because we can only put in 2 decimal places into our table without doing something fancy. And the closest thing that we can find in our table, we can find 0.9222. That's a little too small. We can find 0.9236. That's a little too big. But the closer one, not much closer, but 1.42. Okay, we know it should really, there's some error coming in here. It should really be a little more than 1.42, but not as much as 1.43. And then we can solve for t. So and rounding off some 17.1 to 3 significant figures, and we don't expect to get any more accuracy than 3 figures. So there's some approximation being done here. Yeah, you had a question?
Why couldn't you use 1.425?
You could. Perhaps better yet, you could use 1.424. But we don't insist that you be that fancy. We are willing to take simply the closest number. However, you have a good point that if we want a little more accuracy, we'll use 1.424. And if you're using your calculator instead of the table, it will probably give you more accuracy. Going back to the picture, it looks plausible. 17.1. Yeah, we knew it was going to be more than 10. 17.1 is, yeah, it's somewhat more than 1 standard deviation above the mean. Well, let me look at another such situation. Move the boards around. We've recently been looking at the central limit theorem. And in particular, as a special case of the central limit theorem, what if we have the average of independent, identically distributed binary variables? So say we have a different random variable, which we'll call x bar. This is the average of some number, say n of them, independent, identically distributed binary variables. With some unknown mean. And for a binary variable, its mean is the probability of being 1. And we don't know the standard deviation either. So assume we use our worst case estimate for the standard deviation. So that means for an individual binary random variable, the biggest the standard deviation can be is 1/2. So we'll use that as our worst case estimate, and then that gives us a worst case idea of what the standard deviation for x bar is. And we've been looking at an equation, well, like the equation up there. The probability that x bar minus mu is less than or equal to some error, epsilon. Well, so again, there are various numbers that are involved here. Let's assume that we don't know mu. We're using our worst case estimate for standard deviation of an individual binary variable. But if we know any 2, of the three numbers n, that's the number of things we're taking the average of, the error epsilon, and the probability c. Think of c as standing for certainty. It's our degree of certainty. If we know any two of these three, we can find the other one. So, for example, in the practice test, there's a solve for epsilon one of these. Of course, we could have written this in a way to look more like the equation at the upper board. It's saying that x bar is between mu minus epsilon and mu plus epsilon. But there's a solve for epsilon problem on the practice test. There are, I guess, 3 homework problems of solving for n. And there may have been some problems of solving for the degree of certainty c, and here's another one. Suppose, for example, n is 900, epsilon is 0.01. So, in other words, the random variable x bar we're looking at is the average of 900 independent, identically distributed binary variables, just yes or no. Yes, are you going to vote for my candidate, or no, you're not? Yes, the treatment was successful. No, it was a flop. And what we want is a probability. How certain are we that the distance between x bar and the unknown mean mu for the binary variables, the probability that they're 1, is really small, no more than 0.01. Well, we do this in by applying the central limit theorem. I mean, this is the pill problem. That x bar is normally distributed, almost. So we apply the normal distribution. Its mean is mu, which we don't know. And its standard deviation well, the worst it could be, that is the largest it could be, well, the individual binary yes-no things have standard deviation at worst 1/2, and we have 900 of them. So we divide a half by the square root of 900. We don't need a calculator for this. The square root of 900 is 30. So we have a half divided by the square root of 900. So here we are looking at the probability that x bar minus mu is pretty small, and central limit theorem says we're applying the normal distribution, so we do the usual thing, we standardize things here. Well, we've already subtracted the mean. What we need to do is divide by the standard deviation. The standard deviation of x bar, which at worst is 1 over 60. It might be less than that. And the reason we've done that is that now we have a random variable, call it z, with the standard normal distribution. So we can work with that. .01 divided by 1 over 60, so it's 0.01 times 60. And 0.01. Okay, times 60 gives us 0.6. So we want the probability that something with a standard normal distribution in magnitude is no more than 0.6. Time for the picture. Standard normal distribution, inflection points at plus or minus 1. So we want the probability of being between minus 0.6 and plus 0.6. So this probability we're looking for is that area right there. So we want phi of 0.6 minus phi of minus 0.6. Well, phi of minus a, that's 1 minus phi of a, so let's write it like that. Phi of 0.6 minus 1 minus phi of 0.6. So now we have another phi of 0.6 here. And we can look up phi of 0.6 in our table. .7258. So we need to double this and throw away the 1. We can probably do that without a calculator, although luckily I did it ahead of time so I wouldn't make a mistake. It's around 45%. Okay, yeah, good question. This has absolute value signs in it. And we want to know how to go between writing it this way with absolute value signs or writing it the other way being minus 0.6 to plus 0.6. These are two ways of writing the same thing, and we can go back and forth in either direction. Got to stop for today.